This video is to address week number 7, task number 10. In task number 10, it says what can be said of parallel planes in terms of their slope. I first kind of attributed the situation to 2-space because we've been learning this whole semester that a lot of attributes that occur in 2-space are transferable to 3-space with some changes here and there. But I believe that this is a case that exists exactly as it does in 2-space. Now in 2-space we're dealing with lines because it's 2-dimensional. In 3-space, instead of dealing with a line, we're dealing with planes. But going back to that idea of 2-space, with lines, we can say that our slopes between lines that are parallel are the same slope. I believe that that is true for parallel planes. So looking at some examples, we can basically break it down into 4 cases: horizontal, vertical, a positive slope, and a negative slope. So here we are looking at vertical planes, and if we turn this around and we kind of turn it like this, that's almost a 2-space idea right there, just lines. Now I understand that they're planes, but when we look at it just like that, it breaks it into a 2-space idea, and it gives us that instance of allowing our brain to recognize that that is going to be something that follows suit to 3-space. So parallel planes in the vertical direction are going to follow the same idea as 2-space parallel lines that are vertical. In 2-space, vertical lines that are parallel have slopes that are undefined. Now why is that? Whenever something in math occurs with an undefined nature, we're dividing by 0, and we're going to get that 0 division error, making it in turn undefined because we cannot divide by 0. The reason that this is going to occur also with planes is if we think of our directional slope, the numerator is our change in z, which will be our rise, and our z is looked at in the x direction and in the y direction, but overall it's a rise in the z direction. And if there is a rise in the z direction and we are having values that are continually going above sea level and below sea level, just like we see here, but yet we are never switching in the xy plane to have a value, there is going to be the division of 0. We're going to have a rise occur, but we are never going to have a run. So that leads us to some sort of numerical value in the numerator, but a 0 in the denominator, and that would lead us to undefined. So in the case of vertical parallel planes, we are going to have undefined directional slopes. Okay? The next case is going to be horizontal. Horizontal planes are going to have the same case as horizontal parallel lines. So horizontal parallel planes are going to follow suit with horizontal parallel lines. Horizontal parallel lines in 2-space have 0 slopes. And I think that this is really interesting because we are going to definitely see that what we're doing is we're basically taking the xy plane and we're translating it, which means that xy plane is showing value, okay? But there's going to be no change in the z. So while we do see that the planes hit the z axis, between the surface of either of these pink parallel planes, there is no z being applied that is different from the z that we have. So like, for instance, this plane right here, this bottom plane, has a z value of 1 throughout the entire plane. And in the above plane has a z value of 3 throughout the entire surface of that plane. So there is no difference in the z values at all. What that's going to tell us is that because there's no change in the z direction, there's going to be no rise. There's going to be a value of 0 in our rise. But yet, since our xy plane is basically getting translated, our xy plane is going to always have value. Excuse me. So what we are seeing here is that with horizontal parallel planes, we're going to have a rise of 0 over a run of some sort of numerical value. And what that is going to lead us to is a division of 0 over a number. And 0 divided by any number, regardless of how big or small it is going to result in a 0 answer. So this horizontal parallel plane situation is going to give us a directional slope of 0. The next case is going to be when we see just a positive tilt between the planes, and this is how we're looking at that. And the positive tilt between the planes is basically once you calculate the directional slope, your answer will result in a positive value. So it will give you that positive tilt to the slopes. Okay, so again, using directional slope, using the formula, you would be plugging every value in for your mx, your change in x, your my, your change in y, and then obviously recognizing the rise and run. So you would, your end result would go ahead and be positive. Okay, and then our last case is going to be a negative relationship. And that negative tilt is going to, again, be a directional slope formula. When you compute it and you go through the directional slope formula, you would see that your values would end up being negative. So you would end up with a negative directional slope. So again, in my explanation, I just want to make it clear that I am showing two-dimension ideas of parallel lines follow suit with three-dimensional ideas of parallel planes, and that their directional slope is going to follow the same pattern as the two-space parallel lines formation. Okay, so again, that was week 7, task number 10.